All right, so today we're going to look at some applications of some of the derivative stuff that we've been working on. So it's good to be able to find derivatives, but what are they useful for? What can we use them for? Is probably the more important question. So we're going to take a look at a couple different applications, some in business, there's some like in chemistry as well. Basically anything we want to find a rate of change for. Can be, obviously we've looked at velocities, accelerations, stuff like that. We can use calculus for. So we're going to suppose that we know the value of a car, and it's represented by V at t, V being value in dollars and t being the years after the car is produced. So what is the rate of change of value of the car at 2 years, 5 years, and 7 years? So if we see rate of change, we want to think derivative. So we're going to find V prime at t. And we're going to apply quotient rule here because we have the ratio of two functions. So derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Okay, I'm going to take just a quick couple seconds here and expand and simplify the numerator. So I'm just going to bring in that 0.4, the 6, and also this negative in front into that second bracket. Okay, so the 2.4 t's on top just cancel, and we're left with 19,994, or negative 19,994. So that would be like our simplified derivative for V at t. Okay, so we're going to just use this to find rate of change at these 3 years. So V prime at 2, just plugging in 2 for t. And same thing for 5 and 7. Okay, so I'll give you guys a couple seconds to calculate those. Okay, anyone have V prime at 2? Grayston? So units here would be dollars per year. Okay, V prime at 5. Anyone have that one calculated? Grayston?
Negative 222.1.
Yeah, so 2 decimals for money. 5.6 dollars per year. And V prime at 7. Great. All right, so why are these negative? The value of the car is decreasing. So at around 2 years, the car is losing a good amount of value. As it gets older, it's not really worth as much, so it can't lose like obviously $6,000 in value because that car probably doesn't have much value remaining after the initial drop of the first few years of use for that car, so you'll see it kind of like tapering off as the years go on. Can I scroll from this? Vanessa, Emily, are you guys good, or do you need a second? You're good? Okay. What was the initial value of the car? How do we calculate this? What was that? T is at 0 in the derivative or the original function? Do you guys agree? Kaylin? So if I just want to know initial value of the car and I have a function that tells me the value of the car at time t, I can just plug in a time of 0 into that initial equation, and then I'll have the initial value of the car. So we'll evaluate v at 0. Okay, so obviously here the two second parts are canceling because that's 0 and 0, so we have 50,000 divided by 1. So this must mean at a time of 0, the car is worth $50,000. Okay, any questions so far? Essay? Pardon? Yeah, I mean, if we use the derivative function, we're getting rate of change in the car's value at particular number of years. So if we're just trying to find the car's value at year 1, we can just use the original function. Yeah. Okay, let's move to example 2. Kinetic energy, which is going to be represented by capital K in our equation, is the energy due to motion. When an object is moving, its kinetic energy is determined by the formula K at V equals 0.5 m times v squared. K is going to be measured in joules, m is the mass of the object in kilograms, and v is the velocity of the object in meters per second. So we're going to suppose a ball with a mass of 0.35 kilograms is thrown upward with an initial velocity of 40 meters per second. Its velocity function is the function v at t, where time is t in seconds. Express the kinetic energy of the ball as a function of time. So no calculus involved in this first part. I just want to take my velocity at time function and kind of sub it inside for k at v so that I have k at t instead. So wherever I see velocity in this initial function, I'm actually going to plug in the v at t formula so that I have essentially the kinetic energy at time t. We also have the mass, which we can plug in for m here. Okay, so we're going to essentially plug in k at v at t. It's kind of like the composition of the two functions. I'm going to plug in the mass. And then in place of velocity, I'm doing 40 minus 9.8 t. Okay, so essentially just replacing v with its function v at t. Okay, that will give us kinetic energy at time t. So that will give us k at t. Okay, so here I'm just going to simplify these and then we'll have the equation. Okay, so part B asks us to determine the rate of change of the kinetic energy of the ball at 3 seconds. Now the only way that I would be able to do that is if I had found this kinetic energy at time, because I can't find the rate of change at 3 seconds unless I had plugged in the velocity function inside there. So we do need that function. We're going to determine k prime at t. Okay, and I'm going to be kind of using chain rule and what we call constant multiple rule here. Yeah, Emily? We are going to use the equation from part A.
Are we starting with prime? Or sorry, like the derivative? Like why are we plugging 3 straight?
Oh, okay, so this one says rate of change.
Okay.
So if I just wanted the kinetic energy of the ball at 3 seconds, that's when I would use k at t. Because it's asking for the rate of change in kinetic energy with respect to time, that's talking about the derivative.
Okay.
So when you see rate of change, you want to think derivative. Okay? Yeah, good question. Okay, so we're going to use chain rule here, and we're also going to use the constant multiple rule, and that says that if I have a constant multiple out front of something, we're just going to multiply that by whatever the derivative is. So I'm going to do 0.175. And then we're going to kind of apply like power rule on the outside function here. You're going to bring the exponent down and subtract 1 from the exponent. Okay, so that will leave us with an exponent of 1. And we also have to multiply by the derivative of that interior function. If you really want, you can use product rule here, but the derivative of the first term will be 0 anyways, so that part will cancel out. So we're just going to use that as a constant multiple. Okay, so derivative of the interior function here, what's the derivative of the inside? Negative 9.8. It is a part of the function, but I'm just saying anytime we have a constant multiple, like if you're doing the derivative of 2x cubed, let's say, what do? Well, we keep the multiple out front, and then we apply the derivative of the x cubed part, right? So this is the constant multiple rule. So we bring the 3 down, we multiply it by 2, and we subtract 1 from the exponent. So that's basically what I'm doing here. Yep. Okay, anytime you have just a constant multiple in front of a function, that constant multiple will stay, and you'll just do the derivative of the function part. Okay? So just expanding and simplifying here, we're going to get, if we multiply these things together, we're going to get negative 3.43. And then I'll just bring this in to each term. Okay, and we are asked for kinetic energy, the rate of change of kinetic energy at 3 seconds. So then we're going to enter in 3 seconds in for t. Okay, so we should get negative 36.358-ish joules. There's a little bit more though, not just joules. This is the rate of change of kinetic energy with respect to time.
Joules per second.
Joules per second. So it tells us that kinetic energy is measured in joules, and this is with respect to time, so this is in seconds. Yeah, so if you ever are unsure about the units of measurement, look back into the description and you'll see the units there. So whatever you're differentiating with respect to, in here we were differentiating with respect to time, so. Any other questions on that one? No? I can scroll? No? Okay, let me know when. Okay, ROC is rate of change. Are you good, Essay? Okay. All right, linear density. So linear density of an object refers to the mass of an object per unit length. So we can be given a function that represents mass in kilograms, or mass in another unit of measurement. Let's just say maybe x represents some distance along that object, so x meters, let's say. So for the part of the object that lies between 2 points on that object, you can find the average linear density by essentially just doing like slope. So when we're looking for an average, think like about the average rates of change that we calculated for advanced functions. So just like the difference between the y coordinates of the function over the difference between the x coordinates. And then the derivative of the function is actually going to tell us the actual linear density of a particular object. So an example of this could be something like the mass in kilograms for the first x meters of a wire can be modeled by this function f at x. If we're to determine the average linear density from 5 to 8, essentially I'm taking, like if I have a wire along here, I'm taking at 5 meters and I'm taking at 8 meters what the mass is, and I'm finding the change in mass over the change in distance, right? So I want to look at kind of like the over an interval, right? So we talked about in advanced functions, instantaneous rate of change is going to be at a single point. Average rate of change, if I'm trying to find average linear density, that's over an interval of points. So I'm essentially looking at what the density is over that entire interval. Yep.
So if you see average linear density or average linear density, you don't have to.
Right. So for this one, I'm going to take f at 8 and subtract f at 5. So the function's mass at 8 meters minus the function's mass at 5 meters over the change in distance. Yeah, essay? It shouldn't matter as long as you're consistent with which one goes first and which one goes second. So if you wanted to, you could switch these around as long as you switch these around. And you'll get the same answer as we do. Oh, sorry, +1. These. Okay, so we're getting 25, root 25, and root 16. That's nice because we can just find the square roots as whole numbers, and then we can just leave in fraction form here. So 1/3. Okay, when we find an average rate of change versus an instantaneous rate of change, we still have something per something units. So in this case, we found the average rate of change with mass over time. So it's going to be kilograms, or not time, sorry, over distance, kilograms per meter. Emily.
What does that answer actually mean? So does it mean that over that period of time it's gaining a third of a kilogram?
So this, This one is basically just telling us that over this kind of distance in the wire, that on average the linear density of this material in here is about 1/3 of a kilogram per meter. So it's basically just telling us like approximately what the linear density is all the way from 5 meters to 8 meters. Just for that little piece of the wire. Okay, so it's basically, when we say linear density, we're referring to the mass of the object per length of whatever like unit we're using. So in this case, it's per meter.
Okay, so they're just saying that the wire per meter is just like a third of
Yeah.
Okay.
Yep. So it's saying like on average, if we're going from 5 to 6, then it's going to be about 1/3 of a kilogram. If we're going from 6 to 7, it'll be about 1/3 of a kilogram. 7 to 8, 1/3 of a kilogram. That kind of idea. Okay, so to determine the linear density at an instantaneous distance, like 5 or exactly at 8, we're going to use the derivative, right? Because derivatives give us instantaneous at an exact point. Average is more like just the change in y over the change in x over an interval. So I'm going to take the linear density function. Okay, if you want, you can write it just like this with an exponent of 1/2. And we're going to find the derivative, and then we can evaluate that at 5 meters and at 8 meters. So that will tell us approximately at that particular measurement on the wire what the linear density is at those exact points. Okay, so we're going to apply chain rule here. So derivative of the outside, we subtract 1 from the exponent, times derivative of the inside, so derivative of 3x plus 1 will be 3.
So it's just f prime minus f prime over the 2 intersections.
Hmm?
Like, is it, so it's f prime of x2 minus f prime of x1 over x2.
So this actually is going to give us the equation for linear density at any particular point we want. So all we have to do now is just evaluate f prime at 5 and f prime at 8. Emily?
So we're finding the derivative because we're trying to have an equation behind the instantaneous rate of change.
Yes, exactly. So the difference between what we did in the first part is that we were looking for an average from 5 meters to 8 meters. Now we're looking at the exact linear density exactly at 5 meters and exactly at 8 meters. So I'm not interested in over the range what the average is. I want to know exactly at 5 meters what that linear density is. Kaylin?
If we had like root 127 with this one, I want us to leave it like that.
I think for this one we can approximately see what the decimals are equal to and just make a comparison. But if you want to leave it in exact values, if the root doesn't like perfectly square root, then yeah, you can definitely like round it to a few decimals. Okay, I'll try to let you know like if it's a test or something, whether like I'll say round to this or leave as exact value. Okay, so let's evaluate f prime at 5. And I'm going to evaluate f prime at 8. So the follow-up part of this question, the little end part says, what do these results tell you about the wire? Have you guys talked about like homogeneous material in chemistry before? Yeah, so what does it mean for,
You can either have an alloy, or you can have just like pure like
say for steel, you have alloy, you have chromium, you have iron, and you have carbon being enriched with carbon. Or if you have like brass, or it's copper and tin.
So tell me what it means for a material to be homogeneous.
With a homogeneous material, homogeneous with steel is really just straight steel at the end.
Okay, so same, right? Homo meaning same, right? So all the same material, right? So the fact that the linear densities is different at different points in this wire actually gives us information about the material of the wire. It tells us that the material of the wire is non-homogeneous. So we can say, therefore, the linear densities are different at different lengths along the wire. And we can make a conclusion here that the material of the wire is non-homogeneous. Okay, if you find the derivative and you're calculating and you get two of the same linear densities at different points along your object, it could be pretty safe to say that the wire, the material the wire is made out of is homogeneous.
Do you need to state this on the test that it's not homogeneous?
Pardon?
Are there any application questions in the test?
Nah, I'm just doing this for fun.
Is this actually fun?
No, it'll be on the test.
Don't study it, it's fine.
For the application question, are you just gonna keep it like to this type of stuff, like
Pretty much, yeah.
terminology-wise?
Yep. Okay, the last little application that I want to show you guys is a business application. So if you've taken some business courses, I'm sure you've discussed some of these terms before. So you're going to see P at X, so this is going to be the price function. You're going to see R at X, which will be your revenue function. Cost function, C at X, the total cost of producing a certain number of units. Profit function, so if I have my revenue, that's the money that I'm making for selling my units. If I subtract the cost that it took me to create those units, then I have my profit, right? So the extra that I get after I pay for those actual units that I'm selling. In calculus, economists can actually use marginal cost and marginal profit and marginal revenue to give us more information about a particular thing that's being sold, let's say. So they can kind of analyze certain business functions. So if you find the derivative of the cost function, you're finding marginal cost. So that's instantaneous rate of change of total cost with respect to the number of items produced. Marginal revenue, so we can actually find that by finding the derivative of the revenue function. It's the instantaneous rate of change of revenue with respect to number of items sold. And same idea, marginal profit, so rate of change, instantaneous rate of change of total profit with respect to the number of items sold. Okay, so a company sells 1,500 DVDs, so movies, per month at $10 each. Market research has shown that the sales will decrease by 125 DVDs per month for each 25-cent increase in price. Determine a demand or price function. So if you see a demand function, we're talking about price. So there's a couple things that we need to do in order to do this, especially when we're kind of given information like this. We need to do a couple let statements. So we're going to let X represent the number of DVDs that are sold. each month. It's up to you. It's your note. Yes? Okay, we're going to be having P for price, so, or rather maybe cost. No, we'll say price. Be the price of one DVD. And we're going to have an N as well. That's going to be the number of price increases. So this is, we're increasing by 25 cents. So it will be the number of 25-cent price increases. Okay, so with the information that we have, we can create an equation for the number of DVDs that are sold per month in terms of number of price increases, and we can also create another equation that will tell us about the price of the DVD in terms of number of increases and decrease, or just increases in this case. So I'm going to have a first equation, which will be for X, and that's going to represent the number of DVDs sold. So they're going to sell 1,500 DVDs, but if they increase the price, every time they increase the price 25 cents, sales will decrease by 125 DVDs. So we're going to subtract because sales are decreasing with every number of 25-cent increases. So times the number of increases that we've done. That's our first equation. Second equation, I can also determine the price of the DVDs. So they're being sold at $10 each currently, but we're thinking about increasing the price by 25 cents. Depends on how many times we do that, so we need to multiply it, obviously, by the number of times we increase that 25-cent price. Okay, now ideally, I don't want to have two separate equations here. I want to have an equation that represents price with number of units sold rather than number of price increases or decreases depending on the question. So I want to find P in terms of X. So I have two equations. If I want P in terms of X, I can rearrange equation 1 to get N by itself and just plug it in for the N in the second equation, so that I have P in terms of X. That will give me a function P at X, so price in terms of number of units sold. So I'm just going to rearrange equation 1 to get N by itself. And I'm going to take that and I'm actually going to sub it into equation 2 for N. Okay, ideally, again, I don't really want, like, this looks a little bit messy here, so we're just going to clean it up a little bit. That way, if we need to use it for future questions, then we will have. So I'm going to call this the P at X function. And then, yeah, we want to have just like a more simplified version of this. So I'm going to bring in the 0.25, and I'm also just going to kind of like split this up into X over negative 125, and then 1,500 over negative 125. So when I do 0.25 divided by negative 125, we're actually going to get a negative for that term, so I should have put minus. Okay, so I'm actually just reducing this just to start, or combining it, and then I'm just going to bring that in. Okay, there's a bunch of different ways that you can kind of calculate that. So it's up to you, whatever you feel most comfortable with. I'm just doing 0.25 divided by negative 125 to combine those numbers there. Okay, so in your calculator, if you plug in 0.25 divided by negative 125, that will give you 0.002, or negative 0.002. Okay, so this is just a better, more simplified version of what we had up here when we initially subbed in. So that's going to be our price function.
Should that very first line be PX or?
Yeah, you can write P at X if you want. Nicole?
You can sub this in however you want, right? Like it's slightly different.
Like distribute or whatever?
Yeah.
Yeah. Lots of ways that you can get to the same answer.
Do you have to reduce though?
Yeah, I think like we're going to be using price for other things. So I think if you don't simplify that, you're just going to make your life more complex for like future calculations. So I personally would if I were you. Okay, any other questions on this one? Okay, so whenever we do a price function, like if you look back up at the terminology here, we usually want P at X. So price in terms of number of units rather than number of increases or decreases in price. Okay, determine the marginal revenue when the sales are 1,000 DVDs per month. So first, I need the revenue function, obviously, in order to find marginal revenue. So revenue is actually going to be equal to the price times the number of units sold. So if X represents number of units sold, it's just going to be X times the P at X function. Okay, so P at X, we just found this above. And I'm just going to distribute this to make our derivative a little bit easier so that we don't have to really do product rule. Okay, and then marginal revenue. So marginal, when you see this, you want to think derivative. So that's going to be the derivative of the revenue function. Okay, so just applying power rule there. And then we're going to calculate at 1,000 DVDs. So we should get 9. Okay, and if we're using proper units of measurement here, when we find revenue, we're talking about the change in revenue with respect to the number of units sold, and revenue, of course, is measured in dollars. So this is going to be $9 per DVD. So our interpretation here can say for marginal revenue that when 1,000 DVDs are sold, the revenue, if this is positive, is the revenue increasing or decreasing at this point? It's increasing. So that's probably good. The revenue is, oh, sorry, missed is. at a rate of $9 per DVD sold. Okay, so marginal revenue, just find the derivative of the revenue function. Revenue you can find by multiplying x by your price function. Can I scroll from this? Okay. The cost of producing X DVDs is told to us by the function C at X. Determine the marginal cost when production is 1,000 DVDs per month. So again, we see that word marginal. We want to think derivative. So we're just going to find C prime at X. So just applying power rule here. Most of the time, the cost function is going to have to be given to you. So you won't have to worry about like creating the cost function yourself. And then we're going to evaluate C prime at 1,000. Okay, so from the first part here, we get -8. -8 plus 9.2 is 1.2. Okay, so this is, again, dollars per DVD. So our interpretation here should be that when we produce 1,000 DVDs, the cost is increasing by $1.20 per DVD. Okay, if you see a negative, that means it's decreasing. Can I scroll from this? Okay, last two parts here. Determine the actual cost of producing the 1,001st DVD. So actual cost is just going to be the cost of producing 1,001 DVDs minus the cost of producing 1,000 DVDs. That's going to give me that 1,001st DVD's cost. So we are going to take the cost of producing 1,001 DVDs and subtract the cost of producing 1,000 DVDs. I should get the difference between the costs there. So you're just going to evaluate inside the cost function that was given to you. Okay, and then you're going to subtract that same function, but $1,000 entered in there. That's fine. Did I miss something? Oh, yep. Thank you. Yeah, so if you're copying what I did, I accidentally put 1,000 here. It should be 1,001. Okay, so you're just going to essentially, if you wanted to, you could plug that entire thing in and calculate, or you can do it piece by piece. If you're calculating just like in your calculator, you should get approximately 10,201, and then you're going to subtract by 10,200, and we get about 1.196. Okay, now sometimes we would round values like this, but since this is kind of like very honed in on like a particular cost of a particular DVD, a lot of times like we do actually care about that like fraction of a cent. So I'm just going to leave it kind of like that because it's so like minuscule between like DVD to DVD that fraction of a cent actually does kind of matter. So you can say therefore the cost of producing the 1,001st DVD is about $1.196. Okay, the reason why I also wanted to leave this kind of like fraction of a cent here is so that we can just make a quick comparison to marginal cost that we calculated in Part C and the cost of producing the 1,001st DVD. So what do you notice about the actual cost of producing the 1,001st DVD versus the marginal cost at 1,000? Pardon? Yeah, and it's very similar, right? So when we find marginal cost, we're essentially just finding the cost of producing like additional DVDs, right? So these should always be, when you find the cost of like producing the next DVD, let's say, or the next item, it should be very close to your marginal cost of the number right before it. So we're just going to make a quick little note about that.
If we had a question like this on our test and we got the first, like the price function wrong, would you give us everything else wrong?
I usually account for that, so if you've kind of done the correct process for the rest of it, then you'll get marks, obviously.
Isn't the marginal cost and the, like what we just calculated, they're the same thing? So why do we have them?
Basically the same thing. Yeah, this is like more in like how the cost is like changing, and then this is basically telling us like, oh, the cost of that like next DVD. So yeah, they're always going to be like very, very, very close. On the test? I don't know. I haven't decided yet. Probably like at least like one like displacement velocity acceleration, and then probably maybe 1 or 2 from this.
Oh, that's easy. Displacement velocity acceleration. I didn't understand this one.
Okay, the last part of this is it's asking us to determine the profit function and the marginal profit for the sale of 1,000 DVDs. So if you look above at our information, profit is our cost and our like information with our cost and our revenue. So I need to take the revenue that I've earned from producing and selling X items, and I need to subtract the cost that I have had to put into producing them. So Profit is just going to be your revenue function minus your cost function. Okay, so taking the revenue function from a few questions ago. And then I'm just taking the cost function from earlier. Okay, the reason why I'm doing this is because we're going to have to find marginal profit, so I need to have the equation in order to find that. So once you simplify here, you should get positive 0.02x squared when you add these. Plus 3.8x minus 5,000. This is going to be our profit function. Okay, the question asks us to evaluate profit when 1,000 DVDs are sold. Okay, so we should get 800 from this. So the profit from the sale of 1,000 DVDs is $800. And then marginal profit is going to tell us how the profit is changing with respect to number of sales or number of items sold for the sale of 1,000 DVDs. So we're going to find P prime at X. Okay, the derivative work isn't challenging here. It's more just like knowing what profit is, knowing what marginal profit is, and that kind of stuff. Okay, so just applying power rule here. You should get the marginal profit function of 0.004x plus 3.8, and then we're just going to evaluate that at 1,000.
So this is making $7 million.
Yeah. When you sell 1,000 DVDs. Okay, because that will change if you sell a different number of DVDs. So just make sure you state that. Okay, so if 1,000 DVDs are sold, is the profit increasing or decreasing? Okay, that's always good, right?
Do you want a word answer for every,
For an application, yes. I do want you to interpret that. Yep.
there's like practice problems for all this, right?
Pardon?
So there's extra work for all this, right?
Yep.